2/3 of our body is composed of water, that is H2O molecule. And if you see in this H2O molecule, 2/3 of this molecule is hydrogen atom. So hydrogen atom is abundantly present in our body everywhere. And what is hydrogen atom? This is proton, and in its orbit electron is spinning. So both proton and electrons are constantly spinning, and this is giving motion to the atom as a whole. So all the hydrogen atoms in our body are constantly in a spinning motion. What is a spinning motion? When you rotate or spin a spinning top like lattu, that we call in our language lattu. So when you rotate it, what happens that it rotates in the vertical axis. So it is rotating like this. So when you rotate multiple lattu, all rotates in a vertical axis. But here in our body, these hydrogen atoms are all rotating in different axes. Some is rotating in x axis, some is rotating in y axis, some is rotating in z axis. So all are rotating stochastically. So two physicists thought that we can align all those axes into only one axis in the direction of magnetic field if we give non-ionizing radio frequency wave. And from this concept the discovery of MRI was done. So let's suppose this is the magnetic field, a strong magnetic field, and in which the patient lies here. So this is the patient, and in his body there are multiple hydrogen atoms, and some is spinning in this axis, some is spinning in this axis, some is spinning in this axis. So those are all rotating stochastically. But when you apply a non-ionizing radio frequency wave, then what happens that all those atoms starts spinning in only one axis. So in this axis all those atoms are spinning like this. So all are spinning in this axis. But when we turn off this radio frequency wave, then those all returns back to its original state. So those all comes in single axis of this magnetic field with application of radio frequency wave. But when you turn off this wave, then those all comes back into the original state of stochastic motion. Stochastic means random motion. So the time it takes from these atoms to come from this axis to this random axis is called relaxation time. Relaxation time. So let's suppose it takes a time t for these atoms to come into its original axis. So we obtain images from MRI at 2 points of time. One is t1 time, another is t2 time. During the t1 time, these all the atoms that were spinning on this axis, let's suppose for example, for illustration, let's suppose it takes about 30 minutes, or let's suppose it takes about 15 minutes to come into this configuration. So we take one image while 10 minutes has elapsed and another image while 15 minutes has elapsed. So total is 15 minutes. So we take one image at 10 minutes, that we call T1, and another at 15 minutes, that we call T2. So this is the T1 relaxation time, this is the T2 relaxation time. Relaxation means these all atoms were under the influence of this radio frequency wave, and now when you turned off this radio frequency wave, now they are relaxing back to its original state. And we construct the images from this in the computer and we see MRI. So now let's see how does MRI looks like. So let's imagine this is the MRI of a brain, and outside is a cortex. We have cortical bone outside. Outside is a skin. Under that is fat. There is muscle, temporalis muscle. then there is bone, and inside that we have meninges, and inside that we have, this is outside is subarachnoid space in which CSF is floating or circulating, and inside is gray matter. These are, what is gray matter? These are collection of cell bodies, and from these cell bodies these myelinated fibers are emerging. So these are all myelinated. So myelin is basically fat. So gray matter means collection of these nucleus, and white matter means these fibers that are forming the internal capsule. And we have, let's suppose this is the ventricle, lateral ventricles of the brain. So if you have seen the section of cerebral parenchyma in anatomy lab, then outside is gray, it looks gray, and inside it looks white. That's why anatomists initially called it is gray matter and it is white matter, because it was looking like that. And in T1 image we also, it looks like same, outside gray and inside white. That's why we call this anatomical image, because it is mirroring the anatomy of the cerebral parenchyma. In T1 image you will see fat as white, muscle as gray, bone as black, and this is the CSF, or here is high concentration of H plus, water, so it will look black. And this is, I already told, this will look gray and inside will be white. So why does there are different shades of colors, white, black? This is actually the signal intensity. From where you get high signal intensity, then it appears more dense, more white. If you don't get signal from that structure, then you get low signal, and then computer won't be able to form image, and that will look black. So you know that what is this bone? Bone is basically calcium. So you won't get signal from bone because it is calcium, it is metal, it is paramagnetic substance. You won't get signal from air because this is mainly composed of oxygen, nitrogens. You know, air is 78% nitrogen, 21% oxygen, so very little H plus ions. So actually MRI is imaging on the basis of hydrogen atoms, but there are few hydrogen atoms, so you won't be able to see clearly if you do lung MRI, because lung is filled with air. From airways to alveoli, everywhere is air, so everything will look black, so you won't be able to delineate the alveoli structures. That's why MRI of lung is not useful. Similarly here bone, I told, this is calcium, very little hydrogen atoms, there is no hydrogen atoms. So wherever there is no hydrogen atoms, it will not give signal. So that's why bone looks black, air looks black. If it is any long time bleed in this brain and it has formed hemosiderin, then it is composed of iron, so it will also look black because there is also no hydrogen atoms. Wherever there is high concentration of hydrogen atoms, it will give high signal, but if there is no hydrogen atoms, it will not give signal and it will appear black. So that is the principle. Now let's discuss about T2 signal or T2 image. So this is the T1 image, and now let's say this is the T2 weighted MRI, and this is the fat is looking white because it gives high signal, and bone, I told bone is composed of calcium, so it looks black because it won't give signal, there is no hydrogen atoms. Similarly this CSF contains more hydrogen atoms, that's why it will give more signal and it will look white in T2. In T2 image CSF will look white, and here initially there was gray and white, but it will become opposite here. Why was it white initially? Because there was more fat content, more myelin content here. And why was it gray? Because there was more H plus content, hydrogen content, because of the more water content outside. But in T2 image, it becomes white gray. It becomes opposite of this. Or if you say it gray, then you have to say it more gray, because inside looks more black compared to outside. Here inside was looking more white compared to outside, but it is opposite of this. If we have seen the CT of head, also we can see white outside and gray inside, but anatomically white matter is outside and gray matter is inside, but it looks opposite of that. If you have seen CT, then you might know outside looks black or white even though there is gray matter, but inside looks gray even though there is white matter. So similar to CT it is looking, but then you may confuse whether it is CT. So how will you differentiate? I told that bone looks black, but in CT is ionizing radiation, X-ray beam, it will be reflected by bone, so it will look white. But here bone is not giving any signal because there is no hydrogen atoms there, so it will look black. So one trick is that if you get confused, look at bone. Bone is black means MRI, bone is white means CT. So here it is looking more white outside and inner gray, and it becomes white. The CSF becomes white and the fat is already white. If you suppress fluid inside the CSF, then it is called fluid attenuated inversion recovery. You can suppress either fluid or fat. Here we suppress the CSF because it is looking white, or let's suppose there are sclerotic plaque adjacent to these ventricles. You know there are periventricular plaques in multiple sclerosis, and since it is looking white, so it will merge with this and you may not be able to distinguish. So if you suppress this, suppressing means it now looks black. So if it is looking black, then what happens that you will be able to distinguish the white sclerotic plaque outside. No? So this is fluid suppression. Similarly, we can suppress fat also. Like if you have seen MRI of the femur, those are done in a vascular necrosis of femur or femur fracture. So when there is femur fracture, neck fracture, what happens that there is bone marrow edema. But you know that bone marrow also contains fat. So fat looks white and edema also looks white. So you won't be able to distinguish edema in the bone marrow or necrosis in bone marrow. Then you do suppression of fat to look for that. That is called short tau inversion recovery, which means we suppressed fat to look for edema in the bone marrow. Another is diffusion weighted imaging. So in acute stroke, within 6 hours, even if you do MRI, you won't be able to see a stroke, ischemic stroke. There you have to do diffusion weighted imaging. Diffusion weighted. So what is this diffusion? Diffusion means diffusion of H2O molecule. So it works on the basic principle of diffusion coefficient. So let's imagine this is the brain parenchyma and there is some ischemia to this area. So if there is ischemia, what happens that this cell membrane gets damaged and water starts entering inside this and it causes edema. No? So here diffusion of water is restricted because water has gone inside the cell membrane has ruptured, and if you see the Brownian motion of water molecule in this extracellular space, you won't be able to see. That's why it looks white. We call it restricted diffusion. because of cytotoxic edema, water movement is restricted in that area. That's why it is looking white.